All right, so this is going to be part 3 of working with definite integrals and the fundamental theorem of calculus. In this one, we're just going to do some pretty tricky little examples, 3 problems from section 5.7, numbers 11, 15, and 20. So we'll dive right in. And the first example is number 11. This one is going to be taking the integral from -1 to 1 of the square root of 4x plus 5 dx. Because the 4x plus 5 is under the square root, that's what makes this one definitely tricky. We can't split this up into 2 integrals and evaluate them separately because of the square root. But what we can do is think about what's under the square root as some function called u. So u is going to be 4x plus 5. That would make du equal to 4 dx. So if we were to rewrite the expression over here, or the integral, we could say it's -1 to 1 of the square root of 4x plus 5 times 4 dx. That would give us the du that we need, and we'd have the first part of the integrand here would basically be u to the 1/2 power. So we have kind of a u to the 1/2 du. But as you might remember from before, because we had to sort of stick the 4 in here artificially, we're going to have to place a 1/4 in front of the integrand in order for it to all work together and not change it to some new integral. That's probably one of the toughest parts right there. So now if we take the parts that we have just kind of adjusted and put them together, we have u to the 1/2 du, and we can integrate that. That's essentially going to be 1/4 times u to the 3/2 power divided by that same 3/2. But of course, what we're going to do is we're going to end up multiplying by the reciprocal 2/3, and we're going to evaluate that from -1 to 1. We can actually write this entire expression by writing the two fractions multiplied together. 1/4 times 2/3 would give us 2/12, or 1/6. We can go ahead and place our expression back in place of u, so that would be 4x plus 5, which is now going to be raised to the 3/2 power, and we're going to evaluate that from -1 to 1. Let's go ahead and do the math on that. That's going to be 1/6, and then we place +1 in this expression. We'll have 4 times +1 plus 5, that's 9. So we're going to have 9 to the 3/2 power. If you were to evaluate this, you're essentially going to take the square root of 9, 3, and then raise that to the 3rd power. That's going to be 27, minus -1 in the same expression gives 4 times -1 plus 5, that's 1. Square root of 1 is 1, raised to the 3rd power, still 1. So we have 1/6 times 27 minus 1, or times 26. So we're going to get 26/6, or if you simplify that a bit, 4 and 1/3. And that's the value of the integral when we're all done. That's number 11. Okay, so let's try another example. This is going to be number 15. This one's a trig example, and here we're going from pi over 6 to pi over 3, and we're integrating secant squared x plus cosine x dx. This one may look tricky to you because we've got 2 different functions, one's squared, one's not. And so what we can do here is really consider this as 2 separate integrals. We can integrate secant squared x and then separately integrate cosine x and evaluate each one of those integrals over the same limits from pi over 6 to pi over 3. So let's go ahead and do that. If we integrate secant squared x, that would give us tangent x. And if we integrate cosine x, we're going to get sine x. Everything's going to stay positive, and we're going to evaluate that from pi over 6 on the bottom to pi over 3 on the top. And now at this point, we're going to evaluate tangent x and sine x at the two limits. So we're basically going to have tangent of pi over 3 plus the sine of pi over 3 minus the tangent of pi over 6. And then you can either think of it as, plus the sine of pi over 6 in parenthesis, or essentially that sine of pi over 6 is going to get subtracted. So we're going to get something kind of like that. Now the reason I like this example too is to tell you, I would imagine that the AP exam would like to put this example on the non-calculator part of the test and have you simply evaluate all of these values with their exact values and not worry about the decimal approximation. So this is one of those places where those unit circle values come in handy. The tangent of pi over 3 is the square root of 3. The sine of pi over 3 is going to be plus the square root of 3 over 2. The tangent of pi over 6 is going to be minus the square root of 3 over 3. And then minus the sine of pi over 6 is minus 1/2. This in and of itself could be the answer. We can't combine any of those roots together really in any way that's going to be useful, so we could actually leave it like that. We could give a decimal approximation here of 1.521. Either one of those could be considered the value of this particular integral. If you're having some trouble generating those exact values, you should see me and I could give you a hand with some of that. All right, our last example is going to be number 20. And number 20 is going to be the integral from -3 to +3 of 1 plus cosine x to the 4th sine x dx. And this is another one of those places where we're going to have to kind of think about what we're going to integrate. I noticed that if I have cosine on the inside here and I've got a sine x dx, sine x dx could probably function as something like a du for the appropriate value of u. So I would say that we could allow u to equal 1 plus cosine x. That would make du almost equal to sine x dx. All we would need is to put a negative in front of it, because think about what's going to happen when we differentiate sine x dx to get that, or to get our cosine back. So in this particular case, we can kind of think of this integral as the integral from -3 to 3 of u to the 4th du. And the only adjustment we need to make in this case, since we have this negative here in the du that's not found anywhere in the integral, is we can basically either multiply the integral by -1 or place a negative out in front of the integral. That's that same kind of adjustment that we've made before using fractions. We can go ahead and evaluate this. The negative sticks around, and we're going to have u to the 5th over 5. And we're going to evaluate that from -3 to 3. Now we can replace the u with the expression that it's equal to. So we're going to have negative, and that's going to be 1 plus cosine x to the 5th, all over 5. And we're going to evaluate that from -3 to 3. Okay, so now it's basically calculator time, and we're going to evaluate this expression at those two limits. Okay, when you evaluate this correctly, you might be surprised to see that this is going to give you a value of 0. If you graph the function that you started with, the integrand, you might notice it is in fact an odd function. And since we are integrating it over these symmetric limits from -3 to 3, we're not too surprised to find out that it actually turns out to have a value of 0. So there's your 3 examples.